Hi, my name is Loris Crow, and we are executing at Showtime. Zig SHOWTIME is a show and a community for makers, and you can watch the show to learn more about interesting projects, and you can join the Discord server to share what you're working on and to collaborate with other members of the community. And if that's not your style or you're new to Zig, make sure to check the other Zig communities to find one that suits you best. Hello everyone, summer episode, it's hot, so let's move forward. I have some news, and after that we'll start with the first talk. This should be a particularly interesting episode, I think. So I'll try to take not too much of your time. So let's see. News. Summer break is coming, so there will be no Showtime episode on August. We'll be coming back in September. I think the episode for September has already been scheduled, so it's going to be the 4th of September. And it's also going to be interesting because in September there will be some interesting announcements. A few things are happening in the shadows, things that you don't know about yet. Yeah, so I think there's cool things to look forward to. Also, September is going to be meetup season, hopefully. COVID season, meetup season, we don't know, but in any case, meetup season will eventually come, and it is getting closer. And I've already mentioned this in other places, but we have a Zig user map. If you look at my Twitter profile, it's on Discord, it's on a bunch of places. I should have probably put a graphic to it on stream, but you know what? Maybe somebody in chat can actually send a link to it. To the GitHub repository in chat. This map is useful. Like, you don't have to place yourself exactly where your house is. So the point is not to dox any member of the Z community, but knowing, roughly speaking, where people are can be very useful for me to know who to bother and who to annoy about starting a Zig meetup. And Zig meetups are a stepping stone towards eventually Zig conference. So I don't know, keep that in mind. It might be worth putting in the little bit of effort necessary to place a dot on the map. If you're interested in Zig meetups, of course. Let's see, what else? Oh yeah, next week we are going to have a stream, me and Andrew. So you know that the Zig compiler is being rewritten in Zig. Now, unfortunately, moving from C++ to Zig is going to lower the barrier to entry, and it's going to open the floodgates to low-quality contributions, all coming from me. And the first one is probably going to be next week, because Andrew has agreed to coach me into adding a feature that right now is missing. It's a very minor thing. It's an error reporting thing. If you were watching a stream that I did a couple of days ago, I gave up trying to fix that problem during that stream. And that's what we're gonna do with Andrew. So I don't know, might be fun. That's it for my news. So let me bring up the graphics for our guests. So let's see. So this is a group talk about one of the most ambitious projects being implemented in Zig as of date. Today, from the Tiger team, we have Joran, Adrian, Don, and Isaac. I don't want to spoil anything else, so the title is TigerBeetle, 1 million financial transactions per second in Zig. Tiger team, the stream is yours.
On the southern tip of Africa, an engineer sat in an office, noodling on a problem. Not a stark, brightly lit office filled with cubicles and boring furniture, nor yet a gloomy, musty office that smelled of damp walls and busy humans. It was an office in Cape Town, and that means bright, natural light, colorful people, and a sense of opportunity. That engineer was me, and I'd worked in the payments industry for almost a decade. The last few exposed to fast-growing world of cryptocurrencies, working on an open payments protocol called Interledger. And I must say, in all that time, I'd seen a lot of ledgers. And any system that processes payments needs to record these in ledgers and track balances of the impacted accounts. And in most cases, these are implemented as a combination of some sort of generic database or key value store where you store your, you persist the accounts and you keep your shared state. But those are combined with application code where you implement the business logic and, most importantly, the accounting logic and accounting policy. And in most cases, the implementations of these ledgers left a lot of room for improvement. And the reality of payments is that they're a challenging problem domain. It's unique in nuanced ways. In the first instance, financial systems need to be 100% accurate, auditable, can never lose data, which by itself is not unique to payments, but it's a constraint that adds a lot of complexity and cost, especially since payment systems operate as distributed networks, meaning regular reconciliation, dispute resolution, and so on. And those processes add a lot of cost to the system. So with our team and Coil, our company's involvement in the Modulo project over the last 6 years, we've learned that eliminating the need for reconciliation and disputes leads to low cost for the whole system. And that further leads to a more accessible and more inclusive payment system overall. The second challenge with payments, probably the biggest one, is the need to track balances. So when you're processing payments, you need to update balances in real time. And that's really hard to do at scale. Throughput is limited per account. And so updates to the balance have to be done in order, and accounts become your unit of sharding. So transactions that impact the same account just can't be processed in parallel. And so many of the common horizontal scaling and sharding techniques are just impossible when you're doing payments processing. And so no matter how many instances of your processing logic you run, the balance on an account is shared state that has to be locked, updated, released for each transaction in sequence. And so it's very hard to scale a ledger without cutting some corners, sacrificing performance or safety or both. The challenge of scaling is even more accentuated or emphasized when you're dealing with hubs. So payment hubs that are switching payments or acting as payment clearing systems feel this acutely. And we felt it when we were developing the Interledger protocol at Ripple and further developing it within Coil, because Interledger is intended to serve really high volumes of low value payments. That was our goal. And the reason that this challenge of dealing with account-based sharding is emphasized is because hubs or payment switches generally have a very high ratio of transaction throughput to the number of accounts. They hold accounts for peers, not for end users. And so they generally don't have many accounts, but they're processing a lot of volume because they're switching transactions for a lot of peer systems. So obviously, high volume of transactions per unit of sharding means very hard to scale. So I suppose the obvious question is, who needs that problem solved, and why hasn't it been solved already? And why was I sitting in this office in Cape Town noodling on this problem in particular? And the reality for me is that one of global payments industry's biggest flaws is also actually its saving grace. The vast majority of payments are never switched out over global networks. Payments are very siloed. They're stuck in jurisdictions, and they're limited to currencies. And that's one of the reasons why I think cryptocurrencies have become so popular, is because they create this global payment network that's accessible and easily and accessible to anyone and easy to use. And that's how we felt when I was at Ripple, that the future is global, that payments networks need to have global reach. And when I worked at Ripple and now at Coil, we've always believed in this idea of the Internet of Value and the power of the web as a worldwide platform. So when you bring those two together, how do you enable payments on the web that are global? And so, we've always thought of this idea that payments should be able to move as quickly and as easily globally as information does on the internet. And that should allow anybody around the world, as long as you have an internet connection, to do business with anybody else, not just share information, but actually do business and commerce. So our work on the Interledger protocol is the first step towards that future. And then we participated in the Modulo project, and that was a very specific application of Interledger, servicing the poor and people without access to traditional financial services. And combining that with all of my time prior working in the card industry, I'd always seen payments processed using sort of sticky tape and string solutions. Like I said, generic databases and key value stores banked together with application code. And generally, the payments processing itself then required complex back office processes that would take all of that payments data and reprocess it to actually account for it and turn it into financial accounts for reconciliation and reporting. And so my theory, as I was sitting noodling on this problem, was that it should be possible for us to actually record payments as accounting entries. And why couldn't we have, a really high-speed accounting system from the start? What if we had a Xero or a QuickBooks or similar system that could handle 1 million journal entries per second? And then every payment gets recorded and accounted for in real time, rather than this sort of two-phase process that seemed to me to be holding everything back. Anyway, I had been discussing this internally with the team in Cape Town, and we had talked about, Postgres SQL extensions inspired by the work on Timescale DB, and we'd never really gone beyond theories and ideas. And fortunately, as luck would have it, our opportunity to build a high-speed accounting database came along sooner than we'd expected. One of my colleagues, Don, was working on a performance workstream in the Moduloop project. And, I'd met Joran, and Joran joined us because of his, node expertise. And we were really trying to squeeze out some extra performance out of Moduloop stack. And well, I'm kind of getting ahead of myself. So let me leave the story to Don. But first, let me start by introducing you to Don. He's the Tiger team's very own rocket scientist. And he's the only one of us to hold a Guinness Book of Record. In this case, for the highest launched air-compressed rocket. So Don was the guy that saw the opportunity for us to bring this idea we had noodled on into reality by solving the performance problems at Moduloop specifically. And he can explain how the story unfolded from there.
Cool. Thanks, Adi. So speaking of rockets, Adrian is like our resident Gandalf. He's been around, he saw the problem, and he put the team together and sent us off on our journey. And he's always there with sage advice, a wizard's sense of humor, and a few fireworks of his own. So this rocket project was great fun because it taught me that sometimes the simplest solutions are the best and end up being the most elegant. For example, the final design to release the parachute relied on a 15-year-old spring we found in one of those old toilet paper holders. But of course, the most exciting part was actually just launching something high into the air. Anyway, so this lesson served me well when Joran and I were doing the performance work on Moduloop. So in that work last year, we went about tracing all the SQL queries that got executed when a payment is made. And we found that the number was about 20 queries per transaction between two parties. And many of these queries were writes, so the costs of fsyncs were multiplied along with all the associated network hops. So we set about interviewing people and did a survey of the research to see if we could find a better solution. And the best we found was to use stored procedures to do one database query. But this left little room for business logic and provided only one order of magnitude improvement. So we then asked the moonshot question: how could we make the system 100 times faster and 10 times cheaper to run? And the breakthrough for us was realizing that everything is a batch. Whether it's a batch of 1 or a batch of 10,000, everything is still a batch. So this batching is a powerful idea because if your interface has first-class support for batching on both request and response parts, you can then amortize things. You can amortize your fsyncs, you can amortize your network hops, you can even amortize loading your functions instructions code into the CPU's instruction cache if you have a whole lot of the same kind of data you want to run through the same function. So we then decided to test this theory with a minimum viable product, and thus TigerBeetle was born, which we wrote in JavaScript. The MVP proved to be a success, and TigerBeetle had a throughput of about 200,000 financial transactions per second. So now, with the prototype in hand, we needed to decide what language we would write TigerBeetle in. Would it be C, or maybe even C++? Joran, who had done the modular performance work with me, had at that stage been improving his performance on the football field. And luckily for Messi, our resident Gandalf convinced him to turn his attention to improving payments infrastructure instead.
As Don said, I literally bumped into Adrian on the soccer field. Chatting with Adrian after the game, I heard about his experience with Ripple, Coil, and Interledger. And the next thing, Don and I were doing performance analysis on Mojaloop, which was a fantastic opportunity. Working with Don was a great learning experience for me, how to think about methodology up front. Around the same time, I was writing mostly in C for a storage system and also for a static analysis security tool to help Microsoft protect their software release pipeline from 0 days. So for writing TigerBeetle, I felt most comfortable with C. There were aspects of C that needed to be fixed, but without losing the simplicity and power and orthogonality of the language. As a lucky break, Zig was well on the horizon. I think the way to catch a wave is not when you see the surfers already on it, but when you see the swell. This photo is what I think of when I think of Zig. It captures the simplicity, the precision, the style, and the quality. I first saw the Zig swell in 2018 and got excited. I was late to the party and started sponsoring the language in 2019. And then in 2020, Zig looked like an awesome break, the perfect swell. TigerBeetle was going to be written in something simple and powerful like C, and here it was, but with orders of magnitude more safety and remarkable readability. And we started paddling for it and saw that some talented developers had the same idea. And that's how we met Isaac. Isaac's Zig Showtime talk on River last year was fantastic and a huge part of the reason we started writing Zig. Isaac was always there on IRC with a lot of positive energy, helping us out with questions, even talking about TigerBeetle at the same time as we were thinking he could help accelerate the pace.
Like Joran, I've been searching for a language to replace C for my use cases since quite some time. I tried many, but none stuck until I decided to try out Zig for the Wayland compositor, now known as River, that I started working on early in our global pandemic. As it turns out, I really liked Zig, and my first Zig project ever has grown into a tool that I and a growing number of others use daily. Since then, I've also gotten involved with the development of the Zig compiler itself, contributing various features to support River's development, as well as to push the self-hosted compiler written in Zig forward. I was offered the chance to join the Tiger team several months ago. I've been working on TigerBeetle since this past March. But where are we heading, and how do we chart a course?
With the journey begun and the formation of a fellowship, it would befall upon us to chart a course. From the SQL Shire through linear programming, Mirkwood and Maya, towards the distributed dragon and consensus fire of the lonely mountain spire, where waits the bounty gold and protocol of legend untold.
Entomologists who have studied tiger beetles have long found that one of the 10 habits of highly effective tiger beetles is that they begin with the end in mind. If we were to chart a course, what should the destination be? We came up with 3 goals. Safety. How can we make the system safe? Performance. How can we get 100 times more performance with 10 times weaker hardware? Features and experience. How can we make the system easy to use and simple to maintain? The most important of these goals is safety, so let's start there.
Just like in security, where you might start with a threat model, in other words, all the ways you think an attacker might try to attack your castle so you can defend against them. For safety, we started the same way, with a fault model, and in particular the storage fault model, because TigerBeetle can't afford to lose people's money. The network fault model is well understood. However, the storage fault model is less well known and has also seen some earth-shattering research in the last year or two that has shaken the foundations for distributed databases and what they need to contend with. So much so that they must almost reconsider major parts of their design. For example, in 2018, there was what was called F-Sync Gate. This was where Postgres would retry an F-Sync after an F-Sync error, and then discovered that F-Sync on Linux did not work the way they thought it did, with disastrous consequences. They realized that if a queued I/O or buffered write fails to F-Sync and make it to disk, then the kernel marks the dirty page as clean in the kernel page cache, even though the data never made it to disk, so that subsequent F-Syncs report a success. Postgres responded to F-Sync Gate by panicking after an F-Sync error, and many other applications like WiredTiger, MongoDB, and MySQL followed suit in fixing their F-Sync retry logic. However, in 2020, the University of Wisconsin-Madison tested Postgres, along with LMDB, LevelDB, Redis, even SQLite, and found that all of them still did not recover correctly from F-Sync failure. For example, Postgres would panic, but after a panic, it would come back up again, read the write-ahead log straight from the kernel's broken page cache, and base subsequent decisions on data that was never durably written. In another landmark paper that won Best Paper at FAST 2018, called Protocol-Aware Recovery for Consensus-Based Storage, UW-Madison showed that distributed databases do not correctly distinguish between corruption in data written several days ago from corruption in data written just before a system crash. Because they conflate what is called bit rot with a system crash, if they find a corrupt sector anywhere in the middle of the committed log, they delete the rest of the committed log, all the rest of the committed data, just as if it was the last thing written before a system crash. In other words, transactions that committed long ago and that were acknowledged even to the outside world are now suddenly deleted much later without any explanation by the database, leading to data loss. Worse, however, was when they showed that this mistake in local corruption recovery can not only cause a single cluster server to lose data, but can also actually propagate through the global consensus protocol and cause an entire log cabin or Kafka cluster to lose data. The best part of the paper for me was how they showed exactly how to improve the design of a distributed database so that the local storage and global consensus protocol all work together in how they do fault-tolerant recovery. With this technique from UW-Madison, TigerBeetle can maximize disk redundancy to guarantee that committed entries will never be lost, as long as one copy of an entry remains, and that the cluster is unavailable only when all copies are faulty, but not before. ZFS is a hero in this space, and this talk by Jeff Bonwick and Bill Moore called ZFS, the Last Word in File Systems, is well titled and well worth watching. Thanks to UW-Madison, we saw that for a distributed database, your local corruption recovery strategy needs to interact with the rest of the cluster for safety and for availability, which is why, apart from the licensing issue, we couldn't, unfortunately, just run ZFS under TigerBeetle. But we did appreciate how ZFS actively set out to handle misdirected reads and writes. This is where the software or hardware dereferences the wrong disk sector and reads from the wrong place on disk, or overwrites data it was not supposed to overwrite. This influenced the design of ZFS, and ZFS solved the problem by daisy chaining or hash chaining checksums all the way back to the file system superblock. Because all the checksums overlap each other, you can immediately see when data gets reordered. This was such an elegant solution to misdirected I/O, and I think that if you can have this in your fault model up front, it becomes much easier to handle. We've seen an interesting mix of storage faults, broken kernel page cache, local corruption that leads to global cluster data loss, and writes that go to the wrong disk sector. To cap it off, there are also what is called gray failure latency spikes. A gray failure latency spike is just where the network or disk suddenly slows down dramatically with multi-second latency spikes. What took a few milliseconds now takes tens of seconds. It's a thorny problem when things don't fail completely but limp along. You can imagine the effect this can have on your cluster. In fact, in a study by Microsoft Research, the big availability breakdowns and performance anomalies in cloud environments that they analyzed were caused by gray failure rather than fail-stop failure. At the same time, slowly failing components can also return eventually to normal performance levels and often do. For example, a solid-state drive undergoing garbage collection might become many times slower than the other drives in the cluster, but then return to median performance. The challenge with gray failure latency spikes then is that on the one hand, these temporary slowdowns can cascade into major availability breakdowns, but on the other hand, because they're temporary, it's also not cost effective just to replace the hardware. So from the outset, it was important for TigerBeetle to not only have storage fault tolerance, but also have tail latency tolerance, because the upside in solving this is more predictable performance and a smooth experience for the operator.
I suppose no storage fault model would be complete without noting that file system developers are well aware of the issue. We can see this in some of the best file system comments. For example, from the source of XFS, just ignore errors at this point. Also from ext3, error, skip block and hope for the best. Instead of hoping for the best, we want TigerBeetle to handle all these storage faults and also keep on running with predictable performance.
It's time for a quick multiple choice question. Everybody loves a quiz. We wanted to ask the question now to give everyone time to answer. If you're on Twitter, we've started a live poll. You can find it under the TigerBeetle DB handle. The hour grows late, and the shadow of Mordor approaches Gondor. Don's just flicked our power switch for us. The shadow is getting close. If you're on Twitter, we've started a live poll under the TigerBeetle DB handle. So you'll see the poll there, Twitter, TigerBeetle DB. Pop over there, quickly see what you think. You can also drop your answer in the Twitch chat a little later when we come back to it. And the question is, which of the following is the monotonic clock for elapsed time? For example, for a distributed database to measure elapsed time for something we would never recommend, something dangerous like a leader lease, which of the following is the monotonic clock? Is it A, clock monotonic raw? Is it B, clock monotonic? Is it C, clock boot time? Or is it D, none of the above? We'll come back to this in a few minutes after we look at TigerBeetle's network fault model. While the network fault model is much more well known than the storage fault model, it's still tricky.
Because packets may be delayed, packets can also be reordered. And just like our storage fault model, packets can be corrupted and misdirected. Packets can be routed to the wrong address as the network topology changes. We can't assume that a server will always have the same IP address. We might send a message to a server and find we're actually speaking to a completely different cluster. And of course, packets may be lost.
Which brings us to an interesting question. If some network packets can be lost, while others make it through, what happens to network time protocol and clock synchronization during a network partition? Well, NTP stops working during a network partition. With no network time protocol to synchronize clocks, servers could soon start to run wild and get disconnected from true time, with significant drift even during a short network outage. But within a matter of hours, you could find your cluster playing all 3 Back to the Future movies simultaneously. And unfortunately, it turns out that this is really common in the real world too. It's not a problem if network time protocol and your cluster are all partitioned in exactly the same way, and if you can be sure that they both stopped working at exactly the same time. But what if network time protocol and your TigerBeetle cluster don't fail together at exactly the same time? What if you're a bank and you have strict legal requirements for the accuracy of your transaction timestamps? And what if network time protocol stops working, but your TigerBeetle cluster keeps running? And then the TigerBeetle leader jumps a few years ahead. It's a good idea to have a clock fault model at this point. TigerBeetle's clock fault model means that we need a way to detect when there are too many clock faults in our cluster. In other words, when network time protocol has stopped synchronizing the cluster's clocks. TigerBeetle does this with a really elegant algorithm called Marzullo's algorithm, which can estimate lower and upper bounds on accurate cluster time from a number of noisy clock sources. Whenever a TigerBeetle server sends keep alive probes to another TigerBeetle server, it also takes the opportunity to measure the clock offset to the other TigerBeetle server. Then it checks how wide the bound on cluster time is and can clamp the leader's system time if necessary to not exceed the cluster time. This prevents a leader with a clock in the far future from pushing all subsequent timestamps out into the future. For example, here are TigerBeetle's log messages when it sees that 1 out of 3 replicas has a faulty clock. It can see the confidence interval on the clock error, and the faulty clock can then clamp itself to cluster time, so that hopefully a TigerBeetle is never late, nor is it early, but timestamps precisely when it means to. Which brings us to our riddle. Which of the following is the monotonic clock for elapsed time? For a distributed database to measure elapsed time, we believe that the best monotonic clock source on Linux is not a clock monotonic raw. And the reason is because that was only exposed by the kernel, we think, for synchronization protocols like NTP to measure the quartz crystal drift error. And so it can have very little resemblance to the actual passing time. The answer is also not D, none of the above. And surprisingly, also not B, clock monotonic, but rather C, clock boot time. What are the 2 hardest things? Cache invalidation and naming things? Well, we were looking for a monotonic clock, and the name clock monotonic jumped out at us. It sounded just right, like what we needed. But then we read the kernel man page, always a good thing to do, and we saw that clock monotonic stops measuring elapsed time while the system is suspended. For example, I think during a VM migration, which can happen in the cloud. And this would be catastrophic if a database used clock monotonic to measure time for something dangerous like a leader lease, which again, we would never recommend that any one of us try at home. But clock boot time is exactly the same as clock monotonic. The great thing about it is it just also measures elapsed time even while the system is suspended. So this shows how easy it is to make mistakes in our assumptions, which brings us
to
to
human fault model. Sufficiently complex software is nearly impossible to get correct on the first try. Programmers will write bugs on occasion, no matter how talented they are. In order to detect these inevitable bugs in our code, our primary tool is assertions. An assertion tells the compiler that some condition is guaranteed to be true, barring any programming error on our part. In Zig's debug and release safe build modes, assertions are safety checked and guaranteed to cause a runtime panic on failure. To make our lives easier, the Zig compiler inserts many of its own assertions in safe build modes as well, checking for things such as out-of-bounds array and slice access, integer overflow, etc. Although the goal is to write perfect software which has 0 bugs and never triggers assertions, assertions can often turn what would otherwise be a critical correctness bug leading to data loss into a mere liveness bug. When properly used, assertions encode assumptions that the surrounding code is written under, acting as additional documentation that is safety checked at runtime. For example, from our code, this onAccept function has several assumptions that must be true when it is called, otherwise the code will not work as intended. And since these assumptions are subject to changing due to refactoring, this is a way to make our code base much more robust to introducing bugs due to refactoring. As useful as they are, it is critical to note that assertions are not a replacement for error handling. In contrast to bugs in our code, errors may arise which are not our fault. For example, sending data over the internet may fail, writing to a file may fail, the user may provide invalid input. Robust code must account for such errors and handle them somehow, without invoking undefined behavior in non-safety check build modes. This could mean retrying the failed operation, or, for example, simply panicking. This can be a totally valid way to handle errors in some cases. In fact, TigerBeetle itself will panic, relying on replication and the consensus protocol to recover from select errors, such as if the kernel's monotonic clock ever ticks backwards, or if we encounter an error while writing to disk.
And finally, this is a fun one. Packets may be replayed many hours later. The system has moved on, and our blast from the past arrives to set everything back. And after safety, our next goal is performance. How can we get 100 times more performance with 10 times less hardware?
And how can we get more performance without compromising safety? The concepts of control plane and data plane are often used in networking. You can think of the data plane like a water mains pipeline with huge volumes of data flowing through and nothing inside to obstruct the flow. The control plane, on the other hand, would be all the safety checks you do outside the pipeline as an operator, the little control box that adjusts pressure and decides where the water should flow. In TigerBeetle, we think of the data plane as the work that scales 1-for-1 with the number of financial transactions per second, whereas the control plane is work that is several orders of magnitude less in terms of CPU, memory, network, or storage, but more likely to have catastrophic consequences if gotten wrong. The distinction between the two planes is useful because it allows us to exploit the inverse profiles, where the data plane is optimized for speed of processing and where the control plane is engineered for the safety of that processing. In the control plane, we want plenty of assertions with double and triple checks for safety, whereas in the data plane, we want to optimize for cache misses, context switches, and branch mispredictions. How does this work in TigerBeetle? Well, as a concrete example, we have around 10,000 financial transactions in a batch. A single threaded control plane is responsible for switching each of these batches through the cluster, and we amortize all runtimes balance checks, assertions, and I/O across the batch, so that these become almost free. Yet we have literally hundreds of assertions in the control plane. In fact, we have about as many as the entire Zig standard library at this time, and we're doing an fsync on every single write. Having this clean split between control plane and data plane in the design provides both safety and performance without compromising either. All this helps to keep it simple, keep it fast. There are always compromises. In the case of TigerBeetle, our domain is tightly scoped and very simple, and we want to exploit the simplicity for performance. Batching is the biggest one by far, but here are some more Tiger tricks we've learned along the way. First, we allocate all memory and disk storage TigerBeetle will ever need in advance on startup. This means that TigerBeetle performs 0 allocations at runtime, which reduces overhead in the critical path and avoids handling out-of-memory errors at runtime entirely. We really appreciate Zig's philosophy of no hidden allocations. Next, we make a trade-off and limit ourselves to little endian architectures so that we can avoid byte swapping in our network and storage protocols. Since we also use fixed-size data structures for everything, this means we can simply reinterpret the bytes received over the network as a struct without any copy or other deserialization overhead. These fixed-size data structs are all aligned up to a 64-byte cache line to avoid straddling cache lines and to avoid false sharing, and are 1 or 2 cache lines at most to conserve per-core memory bandwidth.
Without blocking I/O or locks to block the CPU and slow things down, a big bottleneck for TigerBeetle is the CPU being blocked on blocking memory I/O. One way to think of memory is just as a slightly faster disk. It's probably a good way to think of memory like that. because compared to the CPU, main memory is really slow. So we try to avoid cache misses as much as possible. One way to do that is to avoid mem copies. We don't always think of a mem copy like this, but as far as I understand, to some degree, it uses up and flushes your L1 through L3 cache. So reducing or amortizing mem copies in the data plane not only saves CPU cycles, but also speeds up subsequent loads by not thrashing the CPU cache in front of main memory. In the same spirit, another big win for reducing cache misses is something as surprising as direct I/O. That's because we no longer need to spend CPU cycles or CPU cache on doing mem copies again to the kernel's page cache, which we also want to avoid for safety. We get a roughly 7% throughput win just from direct I/O. With some storage devices like NVMe devices so incredibly fast these days, doing a synchronous syscall into the kernel is actually now on the same order of magnitude as the latency of an I/O operation, 1 or 2 microseconds, which is the cost of the context switch into the kernel to make the syscall and the cost of the context switch back out to user space to return the result. It's the there and back again cost. There's a real opportunity cost to syscalls. What if there was a way to submit I/O into the kernel, but without syscalls? What if instead of doing a syscall, we could help ourselves to another I/O instead? We also try to avoid the complexity, rest conditions, locks, and context switches of multi-threading. We just think multi-threading is too hard for us. Instead, we use the kernel thread pool as the data plane. But how is this even possible? Thanks to IOU ring, you can now use the same interface for all I/O, networking, and disk. This makes your program so much simpler. You get a unified I/O interface, and you also get to use the kernel thread pool as your data plane, just by dropping commands into a ring buffer and amortizing syscalls with a single IOU ring enter syscall. This amortizes context switches away right down to 0 and has some real performance benefits, especially if you sometimes do sector-sized I/O, like TigerBeetle has to do when it checkpoints the log. Some of our very rough benchmarking that we've done has shown almost a doubling of throughput for these 4 kilobyte sector writes, which is pretty amazing. Along with these goals of safety and performance, there was one more question left to answer before we could embark on the design of TigerBeetle. We had to ask ourselves, what should the features be? How could we make the system easy to use and simple to maintain for operators? In the past, as Adrian said, developers building financial apps had to glue everything together with multiple queries, moving the data back and forth across the network to run business logic. We realized that all this generic SQL work was simply to recreate double entry accounting. This was the second breakthrough for us at a feature level and defined the set of features that TigerBeetle as a database would expose. Everything is double entry accounting. Everything in financial transactions comes down to debits and credits and accounting policy. We asked ourselves, what if we could just make these accounting primitives first-class features of the database? What if we could invert that equation and move the code to the data to enforce the accounting policy needed to transfer thousands of amounts between accounts, but all in a single database query? What if TigerBeetle could do double entry accounting like Newton's third law? For every credit to an account, there is an equal and opposite debit from a different account. No tables, no rows. As that really classic post on Hacker News today said, no more SQL, just accounts and transfers between accounts. This would let developers model their financial domain as it is, a chart of accounts. Instead of designing complicated SQL schemas across tables, developers can design a real chart of accounts for the perfect schema to match their domain. With our goals and features in mind, how would we implement the database? What would the actual design look like? For this, we would do nothing revolutionary except stand on the shoulders of giants. Martin Thompson is one of those giants. He was one of the co-founders of Almax. They designed one of the first high-performance trading platforms to do more than 1 million transactions per second using lock-free ring buffers to avoid contention. He coined the term mechanical sympathy, and I've learned a huge amount from reading his blog over the years. It just so happened that in July last year, as we were designing TigerBeetle, Martin did a fantastic talk on the state of the art in financial exchange architecture. He's worked on many of these low latency systems in Java and C over the years, and what follows is more or less the design he described. First, we start with what in computer science is called a replicated state machine. It's actually just a simple recipe for implementing a fault-tolerant service by replicating servers and coordinating client interactions between these server replicas. Like C-types or C-pointed declarations, I find that if you just read it backwards, it makes more sense. So you have a machine, i.e. hardware that fails. It's got some state on it, like a hash map, and you then replicate this for fault tolerance. Replicated state machine. What does this look like in practice? So you can make an RSM in 3 easy pieces. First, you append the command to disk, and you can imagine this is exactly like Redis, how it writes commands to its append-only file. Next, you replicate the command to another disk, hopefully on another system. And finally, you apply the command to your state, for example, by updating your hash table. The only thing you need to make sure is that you do these 3 steps in the same order everywhere so that each machine arrives in the same state. Then if a machine crashes, you can catch up and replay the log to get to the same state. This will give you the highest level of consistency, what Carl Kingsbury of Jepson would call strict serializability. This is really the gold standard of consistency, and there's nothing higher. Within a machine, in TigerBeetle, we keep the log order the same by daisy chaining or hash chaining our log entries, just like ZFS, so that we can detect and recover if the kernel or firmware reorders the log by writing to the wrong place on disk. Across machines in practice, if you have a cluster of 3 machines, and if you can make one of them the leader, then you can have this leader order the way in which commands are appended to the log. But what do we do if the leader fails? When the leader fails, we can elect a new leader using what is called a distributed consensus protocol. And that's just something that lets you guarantee that the majority of the cluster have consensus on who the next leader should be. We found that the simplest way to do this is with the view-stamped replication consensus protocol invented by Brian Oakey with Barbara Liskov and later revised by James Carling. View-stamped replication pioneered the field of consensus in 1988, a year before Paxos, and provides the same consensus guarantee as Paxos or Raft, except with a huge advantage that you also know who the next leader is going to be. There's no confusing randomized voting process. Instead, it's just a simple modulo function of what is called view number. Each server starts with a view number of 0. When it doesn't hear from the current leader, it bumps its own view number, and all the other servers do the same. If a majority of servers now share the same view number, then the next leader starts operating. We found you can also squeeze this deterministic leader election idea for some really cool performance optimizations, which we will be documenting in our repo in the next few days. The 2012 revision of the protocol is the perfect place to start if you want to take something like Redis and make it fault tolerant. And to help you do that, we're also making TigerBeetle's view-stamped replication implementation completely generic over the state machine in the next few weeks. So you can plug and play and be up and running with your own state machine, but with all the fault tolerance that TigerBeetle's implementation of view-stamped replication already provides. Every language gets a consensus protocol written for it eventually, but we're hoping that Zig's approach to safety, precision, and remarkable readability are going to make Zig a truly outstanding language for writing distributed without factoring Zig's superpower, its unique ability to comp time.
The way we've structured our code separates the view-stamped replication protocol implementation itself from the lower-level code integrating with the host system and even from the state machine itself. This lower-level code includes abstractions over the system clocks needed, the storage for our log, either on disk using the file system, in RAM, or whatever else you would like to use, and the message passing abstraction for networking based on our message bus. And this message bus merely allows sending messages to a target server or client, which can be implemented over TCP, UDP, even Quick, or whatever else you could think of, maybe Unix domain sockets. We want to do everything locally. And so the state machine is the only part of our code that implements the business logic related to accounting data, which means that you could swap out the state machine, as Jordan mentioned earlier, for anything else you want. And the rest of TigerBeetle's code could theoretically be reused with zero modifications to implement whatever kind of business logic you want for any kind of replicated state machine. And so this is kind of our high-level architecture of our code base right now. And as a bonus, this clean separation of components allows us to do really nice deterministic fuzz testing and automated fault injection. For example, by swapping out the storage implementation with a faulty storage implementation that returns intentionally faulty data on occasion to then test our protocol's ability to recover. And this is what we're working on currently. This is currently not what we have implemented right now, but this is our end goal that we're moving towards. And so the journey to distributed consensus continues as we move TigerBeetle from alpha to beta. I hope to see you all in Zigtember for a special interview and a round table to go deeper into view-stamped replication with pioneers of the protocol themselves, and a $20,000 challenge to see view-stamped replication made famous.
Your one is this it, or is there more?
Yep, that's right.
That's right. Okay, I wasn't sure because now you made me.
The stream is yours.
Yeah, you made me paranoid. Now I was wondering, am I losing packets?
That's the right way to think about stuff.
Yeah. So this talk was incredible. Let me start by saying this. Thank you all so much for the effort that you put in. That was a lot of fun. For real. I think everybody enjoyed it. Also in chat. So I guess this is the moment for people to start asking questions. So you can write them in chat and I'll relay them to our guests. While people come up with questions, I have the standard question, I guess, but since this is it's a group thing and it's also it's a big business project, I have a slight different version than the usual question. Well, so usually ask people, how did you find out about Zig? In this case, what I want to find out is, Joran, I think you were the one who discovered Zig, right? And introduced Zig to the project. Okay, so can you recount the experience of one day going to the office, having a meeting, I guess, or I don't know what the precise setting was, but like the first moment when you sit down to people around the table and you tell them, so I found this language, it's still super alpha, it's made by a guy in New York, he used to work for a dating website, and I think we should build our serious financial database using that language. Like, how did it work? How did you convince them?
Oh, wow.
You're muted. Oh, okay, no, sorry, I can hear you now. Okay. Sorry, you were saying?
I just said to everyone, well, I see therefore a Zig, and that was all cool. And no one ever asked us since then. We just all said, well, we're going to write this in C. And actually saying that, everyone said, no, use Zig, got better compilation chain. They just said, we don't want to worry with like C's build system. Bring Zig. And there was also a lot of drip irrigation going on. So thanks to Showtime, we would be sharing Showtime talks. Andrew's talk on, Zig's awesome async that we shared. We shared like internally about Zig's error handling, how you can, the Zig compiler can actually tell you if you're not handling all the possible errors that the kernel would return. And there was a lot of hype around memory safety. And I'd written in a memory safe language for years, JavaScript. And I knew with the security work I did, that most of the low-hanging security fruit is not actually, complex C buffer overflows. It's all JavaScript. Like, it's JavaScript modules that get exploited and companies get hacked. Even HTML5, you can create a reverse proxy with the old HTML5 app cache. So for us, actually, we all saw Zig as a really safe language, and that was it was so much safer than C, and it was just really like C/Zig. And once we were all on board that C is the language, and obviously Zig is so much better, let's just replace C. It's pretty smooth.
Makes
and
sense.
It's credit to the Coil team, because we also do a lot of Rust, but we wanted this to be a simple domain.
I see. When was that, like in the timeline? I'm thinking of, was this before or after the nonprofit foundation, like the Zig nonprofit foundation?
It was before. So like I said, we were late to the party.
I see.
But it was before. So it was, I think the Zig Software Foundation was founded in July last year, and we were talking about this, I think, just before, like in July, in June, somewhere there. It was concurrent, the same time.
Yeah, I can add there, Lars. So we were. Bjorn has this really cool habit of, when he wants to have like a really detailed meeting, we do walking meetings. And so this was before, there was a lot of lockdowns and so on. So it must have been at least sort of early last year. And I'm not a systems level programmer. I don't know, my background is mostly Java. And so I must say, like, after having worked with Joran for a while and seen, the work that he and Don had done already, like with the Moduli project, he took us on one of these walks and he talked to us about Zig. And I was sort of thought, I trust you, like, you know what you're talking about. And so far, everything I've seen, has been outstanding. So if you believe in Zig as strongly, like he was really passionate about it, as you do, then then I think we should go for it. And I think the sell internally within Coil was pretty easy after that. Like Joran shows a lot of passion for Zig, and that sort of comes through whenever he talks about it. So as he said, like we had a little bit of Rust development happening within Coil, but I don't think Rust was considered for more than 5 minutes once Joran got going. So I think it was a pretty easy call. And one of the biggest motivators was that we were sort of planning to build out TigerBeetle over about a year. So we had, Joran had laid out a really good roadmap for us to get to kind of production ready by next year. And he felt like the trajectory for Zig was going to just map exactly along with us, and that we would probably be ready to release, production level TigerBeetle just as Zig was getting to sort of that level of maturity as well. So stars were aligned, and you had a very passionate Zig promoter in the team.
Nice.
And great leaders, like fantastic people at Coil. Awesome.
I think that was a stroke of genius in a sense, because if it is before the nonprofit foundation, I mean, I was sold on Zig also day one, but I'm also not in charge of a serious database project like yours. There's also that, but I think it makes sense, and the timelines seem to be aligned. That's awesome. So let me think of a couple more questions. Isaac, for you, I think you told us a while ago that you started working with the rest of the Tiger team, right, on TigerBeetle. So the question would be, I guess, how does it feel to have like probably the first, you've taken the first Zig job?
Yeah, it's pretty surreal, but also just really awesome. I mean, I could not be happier to have this opportunity, to be honest. Because like at the start of the pandemic, I just kind of started learning Zig because it seemed like the best language for my compositor, and it really felt great. And so I was kind of like in the back of my head thinking like, should I just be getting better at C? Is that going to be easier to get a job with in the future? Is this really going to pay off? Like getting really good at Zig? And it seems to be paying off. So I'm gonna be more thankful for that, and for also all the work you have done, and you and Andrew have done to make Zig what it is today, and just keep it on this upward trajectory.
Awesome. Oh man, I'm, by the way, I'm also lobbying this also because I occasionally stumble across comments on the internet that says, oh, Zig has 0 jobs. Well, no, Zig has how many of you are writing Zig? 3 of you?
All right. Yep.
Yeah. So at least 3 jobs out there. Amazing.
And we have another engineer in training. She's just joined the team. So Sarah's
Nice.
getting skilled up by the best.
That's awesome. That's very good to hear.
All 4 of us as well on the call, and that's another thing. Like Zig is so readable, so it's almost like TypeScript. Anyone who knows TypeScript, you can read Zig. So again, like Isaac said, it's just all credit to Andrew and to the whole Zig team, because it's just brilliant. Every design decision is just spot on, and it's so awesome. You guys are the ones making
That's
it
a really
all
good
happen.
point. Joran reminds me of something related to your first question, Lars, which when we were so there's a team within Coil building another project called Rafiki. It's all written in TypeScript, which is the main language we use within Coil, and TigerBeetle is a dependency of that project. And so obviously the Rafiki team, the TigerBeetle team have started working closely together. And I loved the first call we had together. One of the other engineers within Coil, who predominantly works in TypeScript, made exactly that comment. He said, wow, I've been looking through the code and I actually understand it. Like I've never read Zig in my life, and it was so easy to understand. So credit to the language, and as well as the work that guys have done. I think even for me as someone who's coming from a Java background, I find it pretty straightforward to understand like what's happening in that code and follow it.
Nice. Don, I have a question for you. So you make rockets, you write Zig code. Is there anything boring that you do? Like, do you occasionally stop and relax and do something generally boring, or is it always high-octane action for you?
No. On the weekends, I'm pretty much a couch potato. Like, just leave everything for the week and then just relax on the weekend.
Right.
I take really slow jogs. It takes me like 45 minutes to do a 5-kilometer loop. So yeah, it's not always high octane.
Okay. Good to know. Okay, let's see. Oh, there's a bunch of questions. Oh my god. Okay, let's go through the questions. There was one from before. I don't want to miss it. Okay, so the first question from LeafView. Will there be support for a non-static server list, and how would it work? I guess this was posted while you were showing the modular system, right? To like the next leader, I'm guessing.
I take it so the question is a non-static server list. In other words, like LeafView, I think you mean, by the way, awesome work that you're doing. Your project is so awesome. I'm watching it on Twitter, and yeah, you're going to leave TigerBeetle's design in the dust. But yeah, the good news is we've got space for reconfiguration of the cluster. So you will be able to reconfigure. You can say, right, here's our list of 3 servers, and you will be able to add servers into the cluster, drop servers. So the ViewStamp replication protocol, especially the one that James Cowling did in 2012, the revision, that shows how to do reconfiguration. So you'll see our VR header has that in, it's called the epoch. But we haven't implemented that yet, and that's still going to be a few months out. For now, it's quite complex. So for now, we're happy with a static cluster set.
Next question from Andrew. Instead of going through all this trouble, why don't you just have eagles fly the money directly between bank accounts? That's a good question. Why don't you just use the eagles, right?
We'll see you in September for the Eagles.
There's a lot of
great question, Andrew. Adrian's probably the best person to answer that.
What, about the Eagles?
Yeah, yeah.
I think why go through all this trouble? I can answer that piece of the question. I think, like I alluded to in my section right at the beginning, I think there's a genuine problem here to be solved that no one really has ever recognized as a problem that they could solve a lot better than the way it's been done in the past. I don't know the deep history of a lot of different databases and why we have relational versus NoSQL versus key value stores and so on, why all these different forms of persistence exist. But somewhere along the line, someone realized they wanted to write a database with a more tightly scoped domain than just storing things in files or something like that. And so I think there's long overdue a data store that is specifically scoped to accounts and transfers, and it's a really nice tightly scoped domain that allows you to write something awesome like TigerBeetle. So it's highly performant, it's very safe, because of that tightly scoped domain. And I'm I love the fact that at Coil the culture is to build stuff like this in the open and make it open source. I really hope people take this and run with it. We're using it, as I said, internally in another open source project of ours. We're helping to make it a part of the Moduloop project. I hope anybody who is trying to solve this problem and has done it before through a weird combination of application code and generic databases has a look at TigerBeetle and gives it a run. I think there's a lot of scope to improve, the way financial systems are built, and I really hope TigerBeetle becomes an important part of that.
We also just figured, these TigerBeetles are so fast. Just tie those payments onto the beetles and send them off, because that's something with the name we didn't explain. But one of the big challenges in Moduloop was because, like, Moduloop is open, it's open source. Moduloop is going to change people's lives in Africa. If we can make it succeed, it's going to lift a whole lot of people above the critical poverty line by giving them access to payments for the very first time, instead of having kilometers, to just do a transaction. Moduloop will let them do banking on their phone. But the thing is that deploying Moduloop, if your database is not fast enough, if it can only do a few hundred payments a second, and if the hardware costs thousands of dollars a month, that's a huge problem. So essentially the equation is, if we can have TigerBeetle, something tiny, just running on 3 office laptops, if that is enough to do 1 million a second, then it means that now someone can actually take Raspberry Pi servers much cheaper and get the throughput they need, because they're not going to need 1 million a second, but it's just an equation that lets you tune your cost, and that brings the operating cost down, which again and the whole idea is we want this beetle to thrive in tough environments. So it's fast, but it's also small and cheap to run.
Right. So basically you're saying that in the end the hobbits should have been riding TigerBeetles instead of walking.
I think they do in the fourth Hobbit movie.
Okay, let's see. Next question from Helios. How are you handling these changes with each version? Are you using one specific version and sticking to it, or updating as it moves?
So until recently, we were tracking master branch, but since the 0.8.0 release, we've now decided to stick with 0.8.0. just to avoid the constant churn of keeping up with master branch, especially since we expect the 0.8.0 to 0.9.0 release cycle to be very, or even more churny than usual as the self-host compiler replaces the C++ compiler slowly. There's already been a lot of churn so far in this release cycle. And so our plan with right now is to stick with 0.8.0 unless it doesn't make sense to do so anymore. And I'm currently thinking that we will probably stick with 0.8.0 until 0.9.0 releases, and then we'll just do the upgrade in one fell swoop and make all the breaking changes at once.
Have you checked, out of curiosity, how many unused variables you guys have?
I've done some. I haven't found any bugs yet, which is kind of surprising, but I haven't checked all the code yet because there's a lot to go through, you know? There's also other breaking changes that are separate from that, but I will definitely be trying to get some kind of automated check for that hooked up to our CI at some point. But yeah, very happy to see that work happening on master branch.
Yeah. Okay, let's see. More questions. Are there more questions? I think we got all the questions. Yeah, I think we got all the important questions. So,
all right.
Everyone, thank you very much for this presentation and for taking the time also to answer questions. That was awesome, by the way, really an awesome presentation. I think I'll leave you each a little bit of time if you want to say anything, and after that we can go on a break. So let's see, who decides the order? Joran, I elect you leader, you decide the order.
Okay, I nominated in the origin story order. So starting with you, Adrian.
Yeah, thanks very much, Loris, for having us. Apologies for my very poor effort at a Gandalf hat. I had a better one and it fell apart literally 5 minutes before the show. So that was the best I could do. But yeah, I really encourage people to join the follow-up call in September. I think it's going to be really exciting, and I've seen the build-up, a lot of what's happening in the background. So I think I'm looking forward to seeing the reaction to that call as well. And yeah, please, track TigerBeetle. As we said, it's an open source project that we hope really makes a difference in how financial services are built and delivered. And as Joran points out, one of the keys for us is building financial services applications that are easy for people to operate, but also cheap. And we hope that has a knock-on effect. Over to you, Don.
Cool. Thanks, Gandalf. Yeah, as Eddie said, thanks for having us. It's pretty cool doing a Zig Showtime talk. Always been just watching it, so it's cool to see what it's like on the other side of it. And it's great team going on. Yeah, I just realized, did we say what the GitHub repo is? If not, it's it's that if you just go coilhq/TigerBeetle, and you'll find it there. Yeah, and then that's about it.
Yeah.
And Adrian was almost, Gandalf the Gold. That would be his Gandalf color. There's many Gandalfs, and Adrian is Gandalf the Gold. With that hat, well done, Adrian, and to everyone. And thank you, Larissa, for the hospitality. This has been since last year. When we decided on Zig as a language, it's Don and my dream goal, to be on Showtime. So it's such a privilege. Thank you. And to the whole Zig core team, keep on. It's phenomenal what you're all doing. And we're supporting you and the whole Zig community. Keep on surfing and keep looking for that dream wave and have the courage just to ride the quality wave. It's such fantastic quality. And see you all again in September.
Thank you. Wait, did I miss? Isaac still has to go, right? Yeah.
I'm not really sure I've got anything to say. I just pretty much kind of want to echo what everyone else has already said and just thank everybody for this opportunity. And thank you to Coil for making me the first Zig developer to be hired just for knowing Zig. And yeah, I'm very excited to see what the future holds for TigerBeetle and Zig.
Awesome.
See you guys in September.
Thank you very much. And so we can We can go to the break. It's going to be 10-minute break as usual. After that, get ready. There's going to be another amazing talk. I just noticed that my countdown was set to 5 minutes instead of 10. Sorry, as usual, my timers are all over the place, so I'll restart it once it reaches 0. It's still gonna be 10 minutes as I said. Sorry. You might remember Isaac from his talk on Ziggler, a very clever and clean way of adding Zig functions to an Elixir project. If you haven't seen that talk, I highly recommend you check it out. And in fact, I also recommend you check out his YouTube channel, where he dives into a lot of the details of how Elixir programs work. Today, Isaac comes to us with another great story. A story of sweat and blood. He fought a war against 44 other languages for us. Did he just survive, or was he able to also bring back glory with him? We all eagerly await his epic tale of implementing a drag race in Zig. Isaac, the stream is yours.
Hey everyone. So this story is I believe the guy named Dave Plummer, who is an ex-Microsoft programmer, retired, has a tech channel, and he posed a challenge for himself initially, where he tried to code a drag race program in C, C++, and Python, just to see which would go faster. So what do we mean by drag race? A drag race means just do some sort of computational task as fast as possible, count how many times it does it, and just benchmark how well you can, how performant you can make the programming language. This is in the spirit of a drag race, where you've got a car and you just want to go as fast as possible on land, and you're not trying to turn curves or do any sort of handling. It's just a straight line. What goes the fastest? So he then opened it up to other programming languages, and so now we have a huge competition between all sorts of different programming languages. They're going to be binned into different types, scripting programming languages, interpreted programming languages, and compiled programming languages. And being a compiled systems level programming language, Zig is in the running just fundamentally to be one of the fastest programming languages. So I won't compare any other programming languages. For that, you have to watch Dave's show. But I'll show you some of the optimizations that went into getting Zig to go as fast as possible. So first, the description of the problem. Oh, yeah. So these were the goals of why I decided to do it. I wanted to show off that Zig can be fast. I also really wanted to show off that Zig is easy to read, and show off the composability features of Zig, and of course, just have fun. So those are my three objectives. And to some degree, we get a little bit of safety just because of the nature of Zig itself. But between speed and safety, I picked speed because that's the point of this. That's the point of this exercise. All right, so let's describe the problem. The problem is called solving the sieve of Eratosthenes, which is a way of figuring out. It's a very old way that dates the ancient Greek times of finding which numbers are prime. I guess in the beginning it was finding whether or not a number was prime. We have much more efficient ways of doing that now, but as a side effect, it tells you all of the primes in a certain space of numbers. So I'm going to go over how that works so you can get a feel for how this algorithm works. So here's the basic form of the algorithm. The first step is we assert that 1 is not prime. So I'm going to take that off the list. Then we're going to look at our list of numbers, and which is a list of prime candidates. We're going to pick the lowest one. In this case, it's 2. And then we're going to smite all multiples of the candidate. So we're going to go down the list and knock all of these guys off. And then we repeat the process. We pick the next lowest prime candidate, and then we smite multiples of that candidate. Now, you might notice here that we have a situation where we may overlap with some numbers that have already been taken out. And that's just part of what you do. There's really no good way of optimizing that. Just go ahead and just get rid of each value in the list. And eventually, you'll be left with only prime numbers, as you can see from the sort of demo here for the numbers between 1 and 20. Okay, so there are a couple of immediately obvious or you might call naive optimizations that you can do. These are mathematical optimizations, and there's one more mathematical optimization that we'll do later, but I'll talk about that in a bit. but these are kind of like not programming language dependent. You can do this in any programming language implementation. So I'm just going to go over with these with you. You should think of these as kind of like table stakes optimizations that everybody's going to do. So the first one is to ignore the number 2. The array only represents the odd numbers, and as a sort of like a micro optimization, you can just consider the first, the 0th slot to be the number 2 and just don't touch that. In which case the transformation between your index and, or between your number and your index is to divide by 2 and discard the remainder, and the reverse transformation is 2 times the index plus 1. And then, like I said here, except the index is 0, in which case we just consider that to be 2. The second optimization is to start sieving at p squared. So if I'm using the prime number 3, then I should not bother sieving until I get to the number 9. And why is that? Because if I have, or let's also talk about 5. So if I am doing 5, then the first number I should start out is 25. Now, why do I do that? Because there's only one prime factor before that, or there's 2 prime factors, 10 and 15, and 15 is already, we know that 15 has already been taken out because 3 was a previous prime. So the first prime that we have to start at is p squared, and that just cuts down your search considerably. Then the other one is to stop counting primes at square root of the size. So why do we stop there? Because you know, the first multiple, like let's say we were going from 1 through 40, and the square root of 40 is something like 4 times something, and sorry, 5, 6. Sorry, so the square root of 40 is less than 7. So we can stop at 5. We don't have to go any further because the first number that we have to consider in 7 is 49, as from the previous rule. So we don't have to bother sieving. So that should hopefully those mathematical optimizations should make sense. All right, so let's go ahead and run this. I've got this all queued up. Let's do, all right. We're gonna run byte. So this is a naive run of the Zig Sieve program, where compiled with release fast, and I'll talk a little bit about that in a bit. It's just gonna go from 1 through 1 million. Which is the target size of the array that we're searching for, and just identify all of the primes, and then loop over again after having destroyed the sieve and started over again. And we do that for over the course of 5 seconds and just see how many of these we can do. And so here is the result. We did it 5,600 times, and I've done it with 2 different data types, Booleans and U8s. And you can see that they're more or less the same. Actually, I find that typically U8 is faster, and for whatever reason on this run, Bool went faster. And I'm not entirely sure where that difference is, which is why I've included both implementations in the standard run. So the cool thing is that I have done it in more than one type, right? So I've used both Bools and U8s as a strategy. Comp time selecting 2 different types to do this, and I'll go over exactly how that happens in another slide. Okay, so or maybe yeah, okay. So how do we verify that this run is correct? So we know how many primes there are in various slices of the integers, and so just the raw count. I know that from 0 to 1 through 1 million, there should be X number of primes, and in release safe, I check that number is correct. But of course, in release fast, we want to be fast, and checking to make sure that you're correct is not part of the criteria. So it just gets compile time eliminated if you're in release fast. This count of how many primes that you have is extremely sensitive to your initial conditions. If you get so much as one thing wrong, that number is very likely to be incorrect. So it's a pretty sound way of making sure that the code that you've written is accurate. And of course, the larger so if you're just checking 10, there's a good chance that it could be wrong even if it gets the right answer. So if you look at the tests in the repository, you'll see that, it gets tested at 10, 100, 1,000, 10,000, and so forth, every power of 10. And so, as you progressively make your code better, you can check off more of those cases. It's actually really fantastic, and having inline tests and being able to write very easy to understand tests is huge point in favor of using Zig. Okay, so if you check out the repo, you'll see this basic layout. Build.zig is of course used to build the system, and it's pretty simple. Main.zig is it contains the main program loop. It has almost entirely just comp time stuff that is used for you to select out whether or not you want to run all, or if you just want to run sort of the focus set that I'm using for the program. Both of which are useful for measuring relative rates and profiling in the course of developing. Then we have sieves, which is the actual implementation of the sieve. You'll see that there's going to be two different implementations that I have, and I'm going to go over the differences between those in a bit. There's runners.zig, which is, if you kind of want to think of it as a runtime. So the challenge includes both single-threaded and multi-threaded, and so I have a runner that can do single-threaded and a runner that can do two different types of multi-threading. I'll talk about both of those in a bit. Alloc.zig contains a custom allocator that I wrote for this program. Wheel is an optimization that I will talk about a little bit later, and I want to keep that one for the last. And then test.zig is just a test suite that I use to make sure that all the components are working correctly. Okay, so let's talk about these four optimizations. So as I alluded to, I wrote two different sieves. One which has an array of bytes that get used, and one that has an array of bits that get used. So it's a bitmap. So and the reason for this is that 500,000 U8s is really big, right? And there's a lot of performance issues that can come about as a result. For example, having to allocate 500,000 bytes of memory in order to use it. So, can we do better? And yes, so we can store content at the bit level instead of the byte level. And one of the interesting things is that there's even a speed optimization that you can do, which is instead of trying to index so one way you could try to find the next prime is you could, see that I'm remember I'm at this index, and then, index into each subsequent bit, and try and ascertain whether or not that is candidate prime or not. But the problem is that is a lot of little sub-accesses between and memory referencing and then masking, and that's a ton of operations, right? And they're dependent operations. So one speed optimization that we can do is we can scan 8 numbers at a time by checking to see if in the case of a U8, if all of the numbers in that small range are no longer candidates, and we just completely skip over that one index inside of the full array. So that's 8 at a time. Or if we are doing U64, it's 64 at a time. Or if we're doing U32, it's 32 at a time. So so those are the two benefits of doing bitmaps versus byte maps. So let's take a look at the speed. So for reference, it's going to rerun the bool. It's going to rerun the U8 case. And here's the bit sieve. So you can see that already it's 50% faster. What you'll notice is that the U64 case is not quite as fast as the U8 case. And I think that has to do with the fact that the likelihood that you'll skip over one of these chunks. So this is a bit sieve that's backed by a U64 integer as your array of bits, as your chunked array of bits, as your chunk in the array of bits instead of a U8. And so the likelihood that all of your candidates in this are there are no candidates in a space of 64 subsequent odd numbers is lower than the likelihood that a span of 8 odd numbers doesn't have a prime inside of it. So you lose an advantage there. And I suspect that if the sieve size were to get bigger, so say 10 million, 100 million, the advantage between U8 and U64 will either close or possibly even flip. So I haven't tested that because it's not part of the competition explicitly. So if somebody wants to try that, we'll have a link to the source code in the show notes. Okay, so the next optimization is going multi-threaded. So I'll talk about two different forms of parallelism. So I call one Amdahl parallelism and the other one called Gustafsson parallelism because there's two different laws that are at operation. So Amdahl's law is that cooperation incurs a cost in their diminishing returns. And Gustafsson's law says that just spray your multiple cores with independent runs. And so Gustafsson's law is roughly linear. Of course, in no real system is it going to be perfectly linear because you'll still have some cooperation events, for example, locking memory or whatever. And operating system will play weird things with multiple cores that you have no control over as the systems programmer. And so the Dave Plummer's original talk does everything with embarrassing parallelism. So what they do is they just run the sieve program and they just spawn threads and then run the sieve program on each of those threads, and at the end they just add together the results and say this is how many times we're able to run it. I also wanted to just play around with Zig concurrency and do one where instead of just doing the naive sort of parallelism, see if I can't write something where they cooperate. And so in the case of the Amdahl's law parallelism, it only works on one sieve all cores only work at one sieve at a time. And what happens is that the main loop first figures out what factor I'm going to work on, and then it leaves behind, here's the next factor to be worked on, and the other cores try to pick that job artifact up, and then leave behind another, hey, here's the next one, and then the next thread comes in and does that again. And the process of picking the next job is locked. So there's a little bit of there's cooperative gating between those events, but everything else is free. So these threads can go and just write to memory willy-nilly, and because the algorithm itself is subtractive, you don't really need to enforce any sort of memory safety, except for preventing use after free when all of the jobs have finished. But that should naturally happen if there are no jobs. There are no jobs on in the queue to be, or not even a queue, in the one slot to be run. So yeah, perhaps unsurprisingly, the Amdahl's law so we're going to run the multi-threaded version. So as it'll again rerun the sieve comparison with U8. There is a speed up if you use Amdahl's law. It's almost 2x, which is, I think, quite good. But even though my system has 8 cores, but you see a much more pronounced improvement when you're doing the massively parallel one. Now, There is an even more of an improvement with the BitSieve version, and I think that that has to do with the fact that there's less memory going on, or there's less memory access needed because everything is scrunched down by a factor of 8. You can't do a BitSieve version of Amdahl because you don't want conflicting writes onto. Well, you could if you made each memory U8 temporarily atomic, but that's really inefficient, so I didn't bother. Okay, so the special allocator. So, in the base case, we've got already 7,000 allocation events. So let's not take trips to the kernel. So I wanted to write a really efficient custom slab-ish allocator. In release fast, runs are backed with page allocator, but in tests, they're backed by testing allocator. So we know there are no memory leaks. And I think that's, one of the nice safety pluses. And also there are no use after freeze, or there's unlikely to be any use after freeze because with testing allocator, use after freeze will typically cause a seg fault, but not always. So I'm fairly confident there are no memory leaks and there's no memory safety issues with the allocator that I've written. So let's compare the two and see whether or not. Oh, right. So by a slabish allocator, how does this work? So when you request a page or a set of pages of memory, it keeps a list of all of the memory units that it's already allocated and have since freed. And if it can find one that has the same size, it simply promotes that to used. And then when it's done, it will demote that pointer back to freed. And if there are no free ones available, then it takes a trip to page allocator and then sends that up. So yeah, it's pretty simple. This is very much a stripped down version of what something like malloc does under the hood. Malloc will try to not give you trips to the kernel, but there is a lot more logic that malloc does because it's not quite as specialized. And one of the great things about Zig is that it gives you the freedom to really create an allocator that is tuned to your use case. And I think that's really powerful. And in this case, it's something you might want to do. So let's take a look at comparing those guys. So again, it will run a few of these different scenarios. And you'll see that in one case, I'll have the base, and in the other case, I'll have it using malloc. So for the single-threaded sieve, it's a wash. For the parallel sieve, the not having a malloc is a real benefit. And so you can see that here. And I think that there's possibly even, and I think for the BitSieve U8, it's a wash. But I think that there's one more optimization that I can do, which is to use thread local variables instead of locking, and that might push this to be even better. Okay. Last thing to talk about is the wheel. This is really cool, and I think that it really shows off some of what really makes Zig awesome. So here in Zigland, we really love comp time, right? And if you look at the code, a lot of the stuff in the main Zig is comp time because I just build these types for these composite types where I'm plugging in a bit sieve into parallel, but also I can plug in a byte sieve into parallel or do it single threaded or doing Amdahl. All those things are composable because at comp time it builds out a unique type for each type of run that it's going to happen. So why not pre-compute some of the primes beforehand and just go for it? So you're going to get. So what you can do is you can just run your sieve over some short span, and then and then just roll that out of your memory. And that'll be a recurrence relationship. And so you just roll that out more than once until you hit 1 million. And then, that'll save you some time because you just don't have to do a bunch of the work going up front. And especially you'll notice that this makes a huge difference with the bit sieve because of the whole skipping process, right? Some of the more expensive runs are the runs where it can't skip as many, especially when you're doing 3, 5, 7. It's not going to be able to skip any of the bytes. But like once you start pre-computing, you already start dropping out bytes that it has to bother to check. So it really makes a huge difference for some of these bit sieves, as you'll see. So what I'm going to do is, this is the only language comparison you'll get. I'm going to show you how it's done in C, and then I'm going to show you how it's done in Zig. So in C, there are these special C files, and what you can see is they've manually dropped in a bunch of this is actually delta encoding. So it says how many steps exist between this prime and the next prime. So there's two problems with that. One, you have to do a seek and then write, and a seek and a write. Whereas with a memory drop, you can just roll it over and possibly use an optimized memory move operation. And you just have to how do we know that this is right? I mean, obviously we're checking our answer, but say this were a 4 instead, right? That would cause a problem, and it's basically impossible to review. By contrast, if you look at the code in wheel.zig, here's what we do. I make a wheel type that is a function of the count, and then how many, and this count is how many of the primes I'm going to use. So I just preceded the first 1, 2, 3, 4, 5. We never use more than 5 primes, anyways. And what it does is it actually goes through and runs the sieve program using a comp time array, basically, and then it runs it just for the set of the primes that we care about, and then it saves the buffer into this template. And then when we run one of the sieves, if it's been instrumented with one of the wheels during the init process, it'll just take that template and copy it out. So this is using comp time to use the exact same algorithm that we're using for the rest of the program in the main program to pre-generate our seeds, which I think is exactly what you want to do to have sort of like a consistent view of all of your code. One little thing that you should know is that Zig puts a cap on how many computational events you can have, or how many evaluation branches you can have at comp time, and so you kind of have to do this little trick here to get it to actually run the entire sieve. Okay, so a couple of more implementation details. Obviously I have to do things. I have to create a different memory layout depending on whether it's a byte sieve or a bit sieve. And the key to understanding that is that I have to do this thing called compression. And indeed, all of these recurrences, because they're product of odd numbers, they won't align to a factor of 8. So what I wind up doing is I wind up dropping in 8 copies of the recurrence, and if you know a little bit of basic college algebra, if you multiply an odd number by 8, you will always get something that's divisible by 8. And so this lets you, by making 8 copies of the of the bit mapped recurrence, you can get something that you can actually fit into 8 bytes. Or there's 8 bits, which is 1 byte. And the last thing is, just be careful. Comp time arrays are a little bit tricky. You have to remember that this is going to get placed in a slot in memory somewhere in your program, and so you have to be careful about treating arrays which are not pointers. They're actually like a block of memory versus what is a pointer to an array, which is a pointer. So just keeping in mind that doing those sorts of manipulations, that's one place where I have to say the reading of the code can get a little bit tricky. What's an array? What's a pointer to an array? And how to handle those correctly. Okay, so let's run it. So these are our reference runs here. And what you'll see is
Isaac, make sure to add some new lines if you can.
Because am I coming up against my...
Yep.
Yeah, let's do this. How's that? So the first number is how many... So the second one is the size of the recurrence and how many primes exist in there. And the first number is how many primes exist inside of that recurrence. And you can see just how tremendously beneficial this is to the number of times we can run it. I mean, already here you're seeing, a several factor jump in the speed. Okay, so last thing I want to talk about is that there is on Thursday, Specs Guy and I took a look at this using Tracy, which was exciting. I'd never done anything to like that before. And we were kind of looking at the performance, just trying to see if we could squeak out any last bit of performance. And I think we're pretty close to being sure that getting any extra is going to be difficult. I think maybe the allocation one might help. But yeah, there was even a case where we thought we could optimize something by removing memory access. And it turned out that probably it's the memory that we were accessing was probably an L1 cache because it's being accessed so quickly. And the latency, even though each iteration had a longer latency, because the CPU is pipelining everything, and can reorder the operations of the actual machine instructions that are going in, because the memory access that we were doing reduced one level of dependency, we could dispatch one operation, one sort of prime search operation every 2 cycles instead of every 3 cycles. And so what we thought would be an optimization turned out to be a pessimization, and sort of this very old school way of having a lookup table where you've got a memory access wound up being a factor of wound up being 30% slower. So I think to me that what was learning for me was that sometimes just having really sloppy old school code might actually be okay, and trying to overthink the problem can wind up, especially if you don't have real data that real profiling data to back up your supposition. You could just be poking in the dark, trying to find something that's based off of a guess when the CPU, which knows better, might do something you don't expect and wind up pessimizing your code. So again, having this sort of pluggable system where building out something where I can do comparisons like this super easily is because of the composability of Zig types, and the fact that they're just hey, I can just write a function that generates a type at comp time, really makes a huge difference. So yeah, Look at the speed up. This is almost an sevenfold speed up from the single speed naive implementation to the parallelized on 8 cores, right? Okay, so that's all I got. Special thanks to Mandayan, who got this all started. I mean, it looks considerably different from what he has, but like I bootstrapped all of my code off of his and got into the challenge because of his solution. And I want to thank SpexGuy for running Tracy with me. And yeah, I'll take questions.
Awesome. So if anybody has questions, please, that's the time to write them down. So Isaac, I've already asked you about Zig, so I'll have to figure out another starting question. I don't know. So I think maybe I have one. So if we were to have one day a first Zig conference in the United States, where would you want it to be?
Well, obviously, I want it to be in the city where I am. It turns out that SpexGuy is like a couple of miles away from me.
Did he like come over?
No, we did it over virtually, but it's really funny. Like,
mm-hmm. So okay, so we can say the state, right? That shouldn't be a problem.
Yeah.
So
yeah,
somewhere
Texas.
In Texas. Okay.
Come to Texas. I mean, I guess it's public knowledge because of the website. SpexGuy's on there. We're in Austin. Come to Austin, everyone.
All right. Okay, so that was cool. How was it like doing the all the improvements? Like, did you feel like you were stuck? Did you always find something else to work on and test your hypotheses? Like, how was the emotional experience of doing this work?
It was pretty straightforward, but always like, there were a lot of times when I did something that I thought was an optimization and then it wasn't, or made it worse. That's always a little bit disappointing because you put considerable amounts of effort into like, oh, how do I rewrite this? I will say that like for a while, I had accidentally gotten overconfident because I had double counted the number of runs, right? Like, so there was a point where I'd switched over from having the count be done by incrementing a pointer to the count, and then originally it was just as sort of the after each run dispatch inside of a while loop, and I needed to do the pointer one to get the multi-threaded implementations to increment the runs, right? And so I was overcounting, mm-hmm. And so, but thankfully I caught that, and it's upstream, or it's PR'd into the drag race. So hopefully, but it made me like, I got to be really careful that like everything that I'm doing is correct.
Yeah. So let's see what people are saying. So people just want to know who's gonna win. So so Andrew is saying, so are we gonna win the drag race? Rat Factor is asking, are you feeling good about Zig's chances in Dave's competition?
I'm feeling pretty good. I mean, I can't say for sure because people can still, PR updates. Just having looked at the Tracy makes me feel really good. Mm-hmm. We really like looked. We really tried. And when your hot loop is dispatching one per 2 clock cycles, that's gonna be hard to beat. Mm-hmm. Now, would the pessimization that we tried out be better for some architectures where some architectures where the system like doesn't do that sort of thing? Yeah, probably. And if I wanted to, I could probably make that be some sort of compiler switch to do one version versus the other. But
Yeah.
you know, I there's just so many ways that sort of like self-management of how many options I want to, you know, have in in sort of the compile time options has kind of like been a thing, right?
Yeah.
Okay, so if you want to know whether or not we're going to win, what I suggest doing is that the Dave Plummer's GitHub repo, which Lars will put in the links, has a Docker container that you can, or a Docker build script that you can run, which will run a comparison between the different programming languages.
Mm-hmm. So I saw a couple of interesting comments. I
actually haven't done that because I don't run Docker.
You're a Docker agnostic.
I just don't like I don't want Docker D to run on my machine. So I use Podman. I use Docker containers with Podman.
Okay, so
I'm one of those guys.
I think there was an interesting type of comment that I remember seeing a couple of times, because we know one thing, that in a recent video, Dave posted, like somebody said, of course, C, C++, or assembly are going to win. And Dave replied, oh, no, you know what? Turns out that right now, neither of these languages is in the lead. And people then immediately replied, well, I mean, of course, it's impossible for another language to win. It's assembly. What could possibly win over assembly? And I think that points out a very interesting point about engineering. Do you want to give a comment on this, or do you want me to do it?
Yeah, I mean, there's just stuff you're not going to do in assembly, right? I think that like writing the fastest thing that I can run on this on my machine, which is like the 8 threads, you know, plus the bit sieve, plus plus the special bit sieve optimization that I have. I think that you would not want to write that in assembler. I mean, obviously you can, because, you know, trivial solution, compile it in Zig, pull the Godbolt, like, you know, copy paste from Godbolt if you want, and then like submit that as an assembler solution, right? You could do that, right? But I think that's like not really the point, right?
Yeah.
Yeah, you know, there's a lot of question marks. Like, you know, Fortran can be really fast at this sort of stuff because it has fewer jumps sometimes. You know, Zig is pretty good at like aggressively inlining, so I don't think that Fortran will beat it. But do I know enough about Fortran to say that for sure? No, right?
At the end of the day, it turns out that it also matters whether there is somebody willing to do the job, right? Yes, in theory, somebody could write an assembly version that can do, at the very least, everything that what the Zig version does. But if nobody does it, then it's not there. And the abstract point of saying, of course, assembly is the fastest language or whatever, it's kind of moot.
Right, and I mean, you can see all of the different optimizations that I've applied, and like really that was easy to like try everything, and then like, you know, try a new thing, new thing, and then just kind of bootstrap it back into the other parts of framework. Like everything was just like really interchangeable parts, and you know, we do it without vtables. So
yeah, that's interesting. Oh, so this is then. The flip side of the coin is, okay, so assembly technically the fastest, although also when it comes to multiple architectures, like there's no metaprogramming, you would have, I guess, to provide multiple solutions, and in practice is a mess. So, okay, but what about the opposite side of the spectrum? So we are here praising the power of metaprogramming and generics, basically, and generics plus, so templates. So why is C++ not winning? I mean, are they still compiling? Is that why?
I don't know. I mean, I think that like to do this sort of metaprogramming stuff in C++, you're typically using objects that have virtual tables, right? And that's already one level of interaction too slow. Maybe Rust has a better chance because everything is done with macros instead.
Yeah.
But macros are kind of clunky, and there's a lot of stuff that we're doing that you can't do with macros so easily.
I think that also for C++, some people, like I'm thinking probably Snectron, if he was here, he would probably say, well, no, I would know how to implement this stuff with like 3-page longer template expressions. So I'm guessing though that they also somehow touch upon some kind of limit there too.
Yeah. I mean, I'm done with templates. If I never have to use templates again, I'll be a happy camper.
Yeah, that was actually also my experience. I once was using the fastest Fourier transform in the West, right? And yeah, got a nice template error. It was like 3 screens of my terminal long, and I said, you know what? I think I'm good. Goodbye.
I mean, let's not. Sometimes Zig types when they vomit on air, they can get kind of long too. So
yeah, we need to find out a way of like containing this stuff, because I think I genuinely remember still my immediate reaction of complete refusal of wanting to deal with a giant template error. We need to find a way of dealing with that.
I mean, I think the other thing is that it's really not the worst in Zig, because you are encouraged to like write tests and stuff.
Yeah.
And worst case scenario, maybe we might need to figure out how to like run a single test inside of a file. That would be awesome. But like, you can at the very least take your test, like, drop it into another file, isolate it, run the test on that one file, and then really kind of like hone in on what the problem is.
Mm-hmm.
So, that one piece of ergonomics, like really, I think helps out a lot. Like I don't think I don't like, despite the fact that we have maybe 3 levels of metaprogramming through Zig's type system going on in this program. I never ran into a situation. I think maybe once I ran into a situation where the type got more than like 2 or 3 lines long.
Mm-hmm. Andrew is suggesting to use test filter. Are you aware of that flag?
No, I'm not.
So you can use that. You can basically run zig test -- test filter, and then you provide the test name. But Andrew, a file name :line option, maybe, I don't know.
Yeah, that would be awesome, because so when I code in Elixir, which has like robust testing, I get this is the line, and this is the file and line that failed in the test result output, and I can just copy paste that and just run test on that one thing, and that's a huge lifesaver.
Oh, so the idea of having like a quick continuation from, okay, so I'm running all the tests, this is the one that failed, let me give me a quick way of running that test, which could be a solution that also is just in the, like, maybe the error message could even suggest that command for you. That would be probably.
Yeah, exactly.
That's cool. Okay, so let's see. Oh, there's a question that I was missing from Salau TV. Let's see. I saw that the code was marked unfaithful at some point. Why was that, and what did you do to fix it?
Right, so 2 problems. I'm glad I had to fix it, because that also got me to fix the double counting problem. Unfaithful. So one was that I was only clearing out the sev between runs, and so they want you to actually go through the process of an init and a dinit, and so in practice that winds up being just shuffling things in an array. or in a slice. So not the worst. They also didn't like that my initial implementation of the custom allocator used scratchpad memory that was allocated in .bss. So it was compile time. It's load time allocated. So when the program gets loaded, it gets, it reserves a certain amount of memory to go. And I mean, I thought about that and I was like, that's not gonna make a difference because we're not measuring end to end, including the command line, right? We're not doing a Unix. We're not doing the time command to measure this. So I was like, it's an unnecessary optimization, and so yep. So I got rid of it.
I see. So just for clarity for the other people that might not be aware what unfaithful means, the idea is that everybody's re-implementing in other languages something similar to the original solution by Dave, right? And unfaithful, I'm guessing, is a re-implementation that it's a bit too far, right? It changes some details that you're not supposed to change.
Yeah. So originally, unfaithful was supposed to mean just the algorithm, the mathematical algorithm. So maybe if you did something like scan one page only, and then move on to the next page, and somehow cache like the primes that you've done. I think that was kind of one of the original examples of what constitutes unfaithful. Or if you use a completely different algorithm altogether, that's unfaithful. Yeah. But they started expanding it to like, okay, these are some other things that we want you to do.
Understood.
Just fine.
Okay, I think we are good. Thank you, Andrew, also for pointing it out. I think that's it. Isaac, is there anything else you want to say before we call it a day?
No, it's been great. Thanks for hosting me again. And I'll see you guys around. Maybe I'll come down to Texas.
Ooh. Nice. Well then, thank you very much, and see you on the next talk, Isaac. Okay, so we are at the end of the show, and what can I say? Have a good August. Enjoy your free time, and be ready to be back in September. We're gonna have a lot of cool things. You saw the final slide from the TigerBeetle talk, right? We're gonna have that. That is gonna be an interesting announcement. There's gonna be other stuff too. So stay tuned, and see you all in September. Bye.